Water distribution systems fall into two distinct categories, open and closed. In a closed hydronic system, the water never interacts with the outside atmosphere. It travels entirely within a continuous, sealed loop of piping. Because this loop is completely sealed, the fluid inside is in a state of constant balance. The water falling down one side of the system perfectly offsets the weight of the water rising on the other side. Flow is disconnected from static head differences, and the circulating pumps provide exactly zero static lift. This diagram outlines 5 fundamental components for a closed loop: source, load, pump, expansion chamber, and distribution system. The expansion chamber uniquely serves both thermal and hydraulic functions, acting as the single point where non-compressible water interfaces with a compressible gas. These 5 components are so physically interrelated that sizing them independently using industry rules of thumb often ignores the complex relationships between water temperature, system flow rates, and piping layout. The design is a series of trade-offs. A change to a hydraulic component like the pump immediately impacts the thermal performance at the load, and a shift in thermal requirements will redefine the pressure requirements of the entire loop. Because of this interdependence, hydronic design must always begin with the thermal load requirements of the building, which then define the mechanical requirements of the pump. This principle is governed by a specific thermal capacity equation. Total heat transfer equals 500 times the water flow rate times the temperature differential. Rearranging this isolates the required flow rate. Notice the mathematical relationship. If the temperature differential doubles, the required flow rate is cut exactly in half. Modern engineering leverages this inverse relationship to save energy. By utilizing wider temperature ranges, such as 14 degrees for chilled water or 30 degrees and higher for heating, designers can drastically reduce the amount of water the pump has to move. The engineering goal is to deliver this precise, thermally dictated flow rate across shifting building loads without causing a hydraulic failure in the distribution system. As water moves through a pipe, it pays a friction penalty known as system head loss. This chart shows the relationship between flow rate and head loss. Because friction increases exponentially with fluid velocity, the system curve bends sharply upward as the flow rate increases. To overcome that resistance, we introduce a pump. Manufacturer pump curves, seen here, represent the mechanical output limits of the pump across different flow conditions. The intersection of these two lines is the operating point. A pump will only ever operate at the exact point where its mechanical limit meets the piping network's physical resistance. If a control valve closes or a strainer clogs, the system curve shifts to a steeper angle. When that resistance increases, the operating point immediately slides up and to the left along the pump curve, reducing the flow. This intersection point is a physical certainty. A pump cannot be forced to deliver a targeted flow rate if the system curve dictates otherwise. Because of how these curves interact, a common assumption persists that if one pump provides 500 gallons per minute, activating a second, identical parallel pump will provide 1,000 gallons per minute. When the second pump activates, we find the new operating point for parallel operation.
Flow doesn't double because system head loss rises exponentially. As flow increases, friction spikes, forcing each pump back along its curve and diminishing its individual contribution. Instead of doubling the output, a single pump operating alone in a parallel setup can often provide up to 80% of the total design flow. This creates a potential hazard for the motor. If a pump sized for parallel operation runs alone, it may push so much water that it exceeds its horsepower, leading to an electrical overload. Adding pumps without graphing the curve intersection leads to significant inefficiencies and miscalculated pressure requirements. There is a similar misconception regarding expansion tanks, that they can be placed anywhere in the loop as long as they have room to absorb thermal expansion. In reality, the expansion tank acts as the absolute pressure reference point for the entire loop. Its function is analogous to an electrical circuit's ground. This defines a rigid hydraulic rule. The pressure at the exact point where the tank connects to the piping will not change when the pump turns on or off. Diagram A shows the tank correctly placed on the pump's suction side, anchoring it at 30 psi. Turning the pump on increases discharge pressure to 40 psi. In diagram B, placing the tank on the discharge side dangerously forces suction pressure down to 20 psi. Dropping the suction pressure can lead to net positive suction head failure. If the pressure falls too low, the water can flash into vapor inside the pump, causing severe cavitation and physical damage. The tank placement dictates the entire pressure gradient across the pump. Putting it in the wrong location leads to the internal destruction of the system. When hydronic designs scale up to large commercial buildings with multiple chillers and boilers, the hydraulic interactions between components become far more complex. If multiple pumps share a loop, they can force each other into series or parallel operation. This interference makes balancing nearly impossible. The consequences are mechanical. A larger pump can overflow a smaller one, stalling flow or creating unexpected pressure drops that damage system components. Standard direct return or reverse return piping is often insufficient to manage the level of complexity found in these multi-pump networks. Large-scale networks cannot operate as single unified circuits. Their internal loops must be isolated to ensure stability. The engineering solution for large networks is compound pumping, also known as primary-secondary pumping. This design relies on a bridge between the source and the load, the common pipe. By keeping this pipe segment extremely short and large in diameter, its friction resistance is effectively zero. This zero pressure drop bridge hydraulically decouples the primary circuit from the secondary circuit, allowing the pumps to operate independently. In a balanced scenario where both pumps move the same volume, fluid bypasses the common pipe entirely, moving directly from source to load. If the source pump provides more water than the load requires, the excess simply travels down the common pipe to mix with the return. The circuits stay hydraulically independent, preventing one pump from transferring its pressure to the other. Efficient hydronic design is not about selecting components in isolation. It is the art of manipulating thermodynamics while strictly controlling hydraulic operating points and pressure references through decoupling.